Today our discussion is on probability density function, or the functions is related to density function, that is cumulative distributions function, right? So we're going to explore more on how to actually apply probability density function and its distributions function, and some of its application. Right, now let's look at this example here. Now we have discussed a few examples before, so these are just extra example that we're going to go through. Okay, example 3 here. We have a continuous random variable x has a probability density functions of given as fx, where it satisfies this piecewise function here. Now our first question is to find the value for c. Secondly, we need to find the capital letter fx, which is known as a cumulative distribution function. And next, we need to evaluate its median. And lastly, we're going to talk about the mod for this distribution function. Okay, now let's get this started. Now, just to recap, any function is known as PDF if it satisfies the following properties. The main properties that it must satisfy would be, okay, just for recap. So for any PDF, it must satisfy these two main properties. The first one being the functions must be greater than 0 for all x that are real numbers. Right? Now, secondly, the total area under the graph must yield a 1. Now, that can be denoted as this. Yeah, okay. So as long as it satisfies these two properties, then we call this spatial function as probability density function. Right? By making use of these properties, we are going to answer the first question here. How do we find the c? Knowing that it satisfies the total area under the graph be equal to 1. Okay, we're going to make use of property number 2, number 1. Right? So to find c, we're going to use this. In this case, it will be c x squared dx. Okay, I think I miss out my differentiation, sorry, my dx. Yeah. Okay, just let me add that on. Okay, now it's okay. Now, even though based on the definitions, we are trying to integrate from negative infinity to infinity, but based on the piecewise functions that we are given, the domain only range from 1 to 4. So we're going to integrate them from 1 to 4. And then that should yield an area of 1 here, because it represents the total probability, which must be equal to 1 here. Right? Now, the integrations should be quite direct to evaluate. That will be this. Okay. And then we're going to substitute all this upper boundary and the lower boundary here. So there will be 64 over 3 c, subtract off with 1 over 3 c must be equal to a 1 here, right? Now here we know that that is 63. So sorry, is that 63? Yes, correct. It's 63 over 3 there, which is 21 c. Therefore, we can conclude that c must be 1 over 21 here. Right? Now that's the first part. C is equal to 1 over 21. Okay, I hope that's clear. Okay, now let's move on to second one. We need to find the distribution functions. This is, just let me write down the definition here. This is known as the cumulative distribution functions, which can be denoted as such. and then given by the definitions of from negative infinity to x, integrating the function ft with respect to t. Right now, that's the definitions for CDF, cumulative distributions function. Okay, now all we need to do is just substitute whatever we have. Since we have obtained the c to be 1 over 21, we're going to write down that as 1 over 21, and then that will be a t squared dt, integrating that from 1, because the lower boundary is a 1, up to x here. Of course, we can't actually integrate that up to 4. If you integrate that up to 4, you are indirectly finding the total area under the graph, which would definitely yield a 1 here. Right? Instead, we are interested to work with the function. We are interested to get the functions, right? So, so from here, the integrations would yield 1 over 21, that is t cubed over 3 x 1 here. So that will be 1 over 63 x cubed minus 1 here. And then there you have it. That's the process that we are going to carry out to work out the distributions function. Right? Now, finally, before we conclude this section here, we must give a full description of this distribution function. Therefore, the full description for this distribution function can be written as such. So for the total area must be equal to 0 for any x value that is less than 1. And then it should be the same as 1 over 63 x cubed minus 1. Okay, given that it's lying, the x value is lying between 1 and 4. And then finally, the total area under the graph must be equal to 1 for any x value that is greater than 4 here. So I hope that is clear for the second one. Okay, now next question, we need to find the median of x. So let's try this out. Median of x. Question. Median of x. Now by definitions, median of x is given as fm must be equal to 50%, where the m represent our median here. Now before we can work this out, I'm going to rewrite the distributions functions one more time for reference, even though I indirectly erase that. I'm going to rewrite that one more time. 1 over 63 x cubed minus 1 for x less than 1, for x lying between a 1 and a 4, and then it's a 1 for anything that's more than a 4 here. So we're going to make use of the distribution function that we have worked out just now. So from here, we can write that as 63. Instead of x, that will be our m. And then that should be 50%. Okay, and then all we need to do is just solve these equations and then obtain the value for m here. Okay, so if I bring this over here, I would be able to get m minus 1 equal to, let me see, 31.5, that should be correct. And then m3 should be 32.5. So just let me check one more time in case I make any mistake here. Yeah, correct. So this one will be 32.5. Now, finally, I need to get the value for median, which is the cube root of this. Alright. Now let me try to get the calculations here. Hopefully, I will be able to work out something. Okay, let us see what we have here. It's 32.5 cube root. So to 3 centimeter figure, it should be 3.19. So this should be 3.1. And then do check 3.19 is fall within this domain. So therefore, the median is actually found within this domain here. And then we are done with number 3. I hope that is clear to everyone here. Now number 4. We need to find the mod for x. Okay, the mod basically means the value of x that produce the largest probability or the largest frequency, relative frequency in this case. Right? Now, knowing that facts, we are going to apply the notations or the definitions to get the mod itself. So the mod, we will let p equal to the mod itself. Okay, the value for p that represent the mod. Okay, so in order to know where this graph would have its highest peak of frequency, we are going to apply differentiations here. So for this case, we will write down df dx. So the differentiations here must be equal to a 0 because this is a method that we use to find stationary point, and then that stationary point shows us a location where the relative frequency is the highest here. Right? So from here, we're going to try this out here, is actually equal to dx. So that is 1 over 21 x squared. So again, to differentiate this, we will get 2 over 21x is equal to 0. And then that directly yield x is actually equal to 0. Now, this indicates that we have the highest value found at x equal to 0. Therefore, we can conclude that the mod, in this case is given by p, is actually equal to 0 there. But we found that this 0 is not actually found within the domain, so there is something wrong with our answer here. So let's check this out. Let me see what we have here. That will be the highest value, right? Okay, so you can see that sometime if you assume that by using differentiation we should be able to reach a conclusions about the mod, yeah, don't get too excited. Now firstly, you might want to check, in this case the mod x value is actually outside of the domain. That's already does not fulfill the requirement for the mod. Secondly, whenever you use differentiations, you might want to check whether you are getting the highest value or you are getting the minimum value in this case. Okay, now to check whether this is a minimum value or whether this is a maximum relative frequency, we can further differentiate this. If you perform the second derivative here, you found that this is actually greater than 0. Then this value x is the minimum value. So the minimum is minimum fx is found at x equals 0. So this is minimum. It does not satisfy the definitions of mod. Mod is defined as a value of x where it indicates the largest frequency or largest relative frequency, or the peak of the function in this case, right? So what is going on, and then how do we actually resolve this? Okay, now I'm going to show you just that. Right? Just let me clear this up, and then we're going to look at how are we going to fix this situation. These situations, personally, I think visual tool would be the best methods to use here. All right, now we're going to sketch this graph. So sketching this graph is not a problem here. It's quite an easy task to work with. So I'm going to sketch this very quickly. So this is fx here. Right. Now we know that the function is given as fx equal to 1 over 21 c squared. Now it passes through here, but anyway, because the domain is set at 1 and 4 here, so at 1 it must be 1 over 21, so somewhere here, and then at 4 it must be 16 over 21, so it should be somewhere here. Generally the graph looks something like this, because the graph only appear between this domain, so I'll just write it down. I'll just draw it in such a way that it cover the domain here. Alright, now that is our functions. From these functions you can quickly discover that the highest frequencies that is found when x is equal to 4. So we found that fx is maximum. This is maximum within the domain x greater than 1 and 4 when x is equal to 4. So when x is equal to 4, yes, we have the largest value here. And then we found that this largest value is actually 16 over 21. Then we can say that therefore the mod is equal to a 4 here. So the mod is found when the value of x is equal to a 4. Alright, so I hope that is clear to everyone here. Alright, let's move on to the next one. Next question here. We are also given a continuous random variable x that has a probability density functions given as such. Now our first part is to find the mean, which is denoted by the symbol mu, of the continuous random variable x, and show that the variance of the random variable x is equal to 0.05. Now that's the first part. Okay. Before we read on the next part, let's try to work out the first part before we move on to the second part of this problem here. We need to find the mean and the variance. Okay, using these probability density functions. Now the mean mu is given as expectations also, and then it's given by these definitions x fx. We're going to integrate that from negative infinity to infinity. Okay, right. But based on this context, the lower boundary is 0, the highest, the upper boundary is 1. So all we need to do is use 0 and 1, and then we're going to apply these functions here to obtain its mean. So it's x multiplied with the functions here. We have x squared dx. Okay, so there you have it. Now from here we can integrate this quite easily. So before that, I just rewrite that properly. That is x3. Okay, now that will be a 2x cubed, and then that will be a 4 and then integrate that from 0 to 1. Okay. Now that is quite easy to work with. It must be a half. Yeah. Okay. I hope that's clear. So the mean or the expected value for x is a half. Now next, before we can obtain the variance itself, maybe it's best if we can work out this expected value for x squared, which is given as x squared fx dx from negative infinity to infinity. Now again, we're going to follow the boundaries here, 0 to 1, and then there will be a 6 x cubed, 1 minus x dx. And then there will be a 6x cubed, 6x 4 there. Yeah. Right. So you have 3 over 2 x4, and then 6 over 5 x5 here. 0 and 1. So basically that will be 15, 12, that will be 3 over 10. So 3 over 10. And then finally, we're going to make use of the definitions for variance. So variance is given as, in this case, they're using this symbol here. It's given as, or it's given by this definition. Okay, so there is 3 over 10. Subtract off with the square of the mean. Alright, so that is typically 0.3. Subtract off 0.25. That will give us 0.05. Now that will be our variance. Yes, we managed to show that the variance is actually equal to 0.05. Right. So I hope that is clear for the first part. We're going to open up the second part and then work it through. Sure. Second part, we need to show that the distribution functions related to continuous random variable x satisfy this piecewise function here. Right? So that's the first part. And then after that, we need to use this result, this cumulative distribution function, to show that the probability of x minus mu lying within that variance is about 15% or 0.1495 in this case. Right? And then finally, we need to analyze what would this probability be instead of x were normally distributed. Yeah, okay, so that's another part that we're going to look at shortly. So this first part, we're going to prove that the CDF for the PDF here is shown here. Right? Now, therefore, we're going to work out the CDF through its definitions. Okay, so fx is given by this. That will be the lower boundary from 0 to x ft dt. Then that would be 6t minus 6t squared dt from 0 to x. Then there will be a 3t squared minus 2t cubed 0 to x, and then finally we get ourselves 3x squared minus 2x cubed. Now that is our distribution functions that satisfy this domain here, where the x is lying between 0 and 1. Okay, now for that we are going to conclude the descriptions for this distribution function. So we can write down the distribution function here is given by 0 for any value that's less than 0 here, and then it should be the same as now if you like to factorize this by all mean, is basically just x squared minus 2x. Yeah, if you like to write that, and then this is only true within this domain, and then finally the total area within this probability density function must be equal to 1 for anything that is smaller than 1. And then we managed to prove that this distribution function is indeed given by this piecewise function. Right? And then next we're going to use this result, meaning that we're going to use this result to show that this probability is given as such. So probability of x minus mean is less than this one here. Okay, now we can start with this. This can be written as x minus mean less than the variance square and then more than the negative variance square. That is the definitions for the modulus. Okay, so from here we can rewrite that, and then we have calculated our mean and variance before. Just to recap, the mean is 0.5 and then the variance is 0.05 as indicated here. So all we need to do is just substitute all this value here. We have x minus 0.5 less than 0.05 more than negative 0.05. Now with a bit of arrangement, we will get, if you restructure this algebraically, we will get, what do we have here? 0.45. So the x is less than 0.45 or less than 0.55 here. Okay. Now that will be our probability that we are interested to find out. And then how are we going to make use of the distribution functions in this case? So we can do it this way. Is 0.55 subtract off with 0.45. So indirectly, we are making use of the CDF to work out this probability here. Okay. Now, just a brief illustration as to what is going on here. Now, assuming that we have a graph here, this original PDF is actually a quadratic function. So when x is passes through 0 and then a 1 here, it's lying between here is a negative graph here. Now most probably the functions will look something like this. For instance, this is the fx, this is x here. Okay. Now what we are looking at is there is a value 0.55 here, and then there is a value 0.45. Now we are interested to find out the area under the graph that is shown here. So what can we do? The first step is to find out the total area here from the starting 0 up until 0.55, which is given by f 0.55. And then once you are happy with that, we are going to subtract off with this section here. And then that would actually yield the region between 0.45 to 0.55. Now for that, all we need to do is just substitute this value here into our distributions function here. And then hopefully we will be able to obtain the result here, right? Now I'm going to use my software here to calculate so that it's much more easier. Okay. Just let me position it nicely first, and then we'll see whether we are able to work this out. Okay, now I'm going to write down the function first. Okay, there's 2x cubed. Okay, that's what I have. And then I'm going to make use of this. Okay, hold on. That's a h. So it should be 0.55. Subtract off with 0.45. And then there you have it. You can see that. Of course, you can leave it as 3 significant figures, but here, just for demonstration, I'll leave it as 2 decimal places. Now you can see that the answer is 0.15. So 0.15 approximately. But anyway, based on the questions, I did not fulfill the requirement. I need to leave the answer like 4 decimal places, so I might want to change my result a bit here. But just let me get back my software one more time, and then just let me configure the decimal numbers that I can get. Yeah, maybe I'll get that 4 decimal places, and then let's see whether I'm actually getting what I'm supposed to get. So that is actually 0.1495. Yes, correct. So now I can write down 0.1495. Yes. Now this time it is proven. So it's always best. It's always good to check back the questions again. So I hope that is clear at this point. Okay. Now we're going to answer the last one. Questions. What would this probability be if instead x were normally distributed? Okay, if x is normally distributed, I'm going to draw the diagram. Is a bell-shaped curve. In this case, is x. Okay, forgive me if I did not draw this bell-shaped curve neatly. So it should look something like this, and then the center, you can say that the center is located somewhere at this value. We know that the center represents the mean itself, so let's assume that the mean is in this case we have already calculated the mean 0.5, and then the variance given as 0.05 here. Now, this is the assumptions that the probability density function can be modeled using normal distributions curve. Okay, this is how it look like. And then what we are interested to determine will be here. We are still interested to determine the probability of x lying between 0.45 and 0.55 after we have changed and restructured this. Now that will be from 0.45. Okay, 0.45 will be somewhere here, for instance. Now this is 0.45 until up to 0.55 here. Now this is the area that we are interested to obtain. If it is a normal distributions, will the answer be very close to this? If it is very close, therefore we can say that these probability density functions could be approximated using a normal distribution. Okay, let's see. Now, of course, in this case, you can either refer to the normal distributions table, or you can get a piece of software to help you to do that. Right? In this case, I'm going to use just that. Right? Just let me clear this up. Okay. Okay, here I'm interested to get the normal distributions. Right. So by using the normal distributions methods, you have to refer to the data booklet usually, or in this case, we can use a piece of software here. All right, now let me see what we have here. We have a normal with the standard deviations, and then variable value, and cumulative Boolean. Okay, whether we are interested to calculate the total area itself or not. Right? Okay, so just let me check for a while. What are we going to get here? Okay, most probably we're going to get this one here. We know that the mean is 0.5. It's not too mean. Standard deviations. Now, standard deviation is the square root of my 0.05 in this case. And then here, I'm interested to get the variable itself, the variable value. Okay, so what am I looking at here? This one will be the value of 0.55. Okay, 0.55, and then I would say here is true. I'm interested to get the area. Okay, just let me work that out. So the mean is 0.5. Standard deviations is 0.05, and then the x value is 0.45. I need to turn that on as true. Okay, and then of course the result will not be that accurate if I don't change my configurations here. Okay, maybe to 5 decimal places here. You will see that this is, or this can be given as such. Okay, just let me. All right. So this can be given by a normal distribution. So you can refer to your data booklet to obtain the normal distributions in this case. The typical way how we carry out the normal distributions. Now, I'm going to show you the step by step in a while. If you are using software, you should be able to get 0.17694 here, or approximately 0.1769. Okay, which is I would say based on your requirement is not too far from this. And then if your requirement is more strict, then maybe this normal distribution would not fit very well with this probability density function. Okay, so I hope that's clear. Now let's show you how do we usually carry this out in the exam, right? A-level exam especially. So this is how we're going to do it. Now the step-by-step methods will be here, 0.45. Before that, we say that x is a normal distributions, assumed to be normally distributed with a mean of 0.5 and the variance of 0.05 here. Right? So anything lying between here, 0.55. Oh yeah, I almost forgot. This is actually less than. It's not equal to. So my bad here. Just let me move that, touch up a bit. So it should be less than. So for this, usually we prefer to turn it into a z-score. That will be 0.45. So 0.45. Subtract off with 0.5. Okay. So 0.45 minus of 0.5 divided by the standard deviation, which is 0.05 square root here. And then that can be turned into a z-score. Okay, from here this is 0.55, subtract off 0.5 divided by 0.05. Okay, so that's a 0 there. Now in this case we will get, I'll try to simplify it a bit, that will be a negative 0.05 over, yeah, basically it's quite easy to write here. You don't really need to write this one here. It's basically negative 0.05 square root less than a z-score less than. This one definitely is 0.05 also, so 0.05 square root. Alright, now that will be the probability that we are going to find here, right? Now next, let me show you how to use the data booklet to actually obtain this result. But before that, in terms of z-score, this is how the shape look like. Instead of using the original setting, in terms of the z-score, if this was z-score itself, and then the graph would look something like this. The mean will be 0 in this case, and then we are looking at a negative value here, negative 0.05 square root, and then another value which is 0.05 square root here. Therefore, we are interested to find out the area under the graph here. And then because it's a normally distribution, therefore both of this region is symmetrical, so therefore the area should be the same in this case. Right? Okay, now we're going to. This is our data booklet. Now, depending on the distributions, the z distributions functions that you are referring to, there are many versions of this normal distributions table that you can get online. But based on the one that we have, this is the configurations. Now, whatever numbers that you read from this table, it represents this area that cover the left-hand side tail of this region. Okay. Now we can check this out. Based on this our configuration here, we are interested to find out the whole area from negative infinity up to 0.05 there. Okay. Now before that, we're going to look at the square root of 0.05. What are we getting here? Square root of 0.05 here. Square root 0.05. Okay, so that is 0.2236. 0.2236. Okay, I'm going to write that down. 0. Okay, 0.2236, and that will be our z-score here. So the first step is to figure out the total area here. The total area from here. So let me represent with a different color. Now we're going to figure out the total area here first. Up to square root of 0.05, which is 0.2236 here. Okay, we're going to read that z-score from the normal distributions table. So that is 0. You can see that from this table is 0.22. Right. I would say based on this table is kind of limited in its accuracy. So maybe we can read it as 0.224 or 223. Yeah. 0. Just let me highlight that. So that's 0.224, for instance. Okay, if you read the 4, it'll be around 15. Here it says addition. So you have to take this value here, 0.5871. So that will be 0.58. I'm just going to write it down here first. 0.5871 plus the 15. So 15 is added on at the end here. Then that would yield 0.60. Yeah, 602. So that is 0.602. Right? Is it 0.602? Did I add it up correctly? 0.571. Oh, oops, sorry. I think I missed out this this section here. Just let me correct that. I think the number is supposed to be this. I don't know. That is 0.58711 here plus with 0.0015, and then that yields 0.5886. 0.5886. So this region here represents an area of 0.5886. And then what we are interested to find is actually this area, this very small area here. Right? So what should we do? All we need to do is, there are many ways to do this. You can either take this area, subtract off with this. These sections of these sections that is marked as in red is 0.5. That's 0.5. Yeah. Okay. So we can actually take 0.5886, subtract off with this. Then we will be able to obtain this very small region here. Yeah. As I mentioned before, this very small region here is symmetrical to the region on the left hand side. So therefore, to answer these questions, we can multiply this region here. So this region will be given by 0.0886. Then finally, the answer for this, the probability for z lying between these two values will be given by, I'm going to write that down, negative 0.05 square root less than z more than, less than 0.05 must be equal to twice of this region here, 0.0886, and then that would yield 0.1775. 2. 0.1772. Okay, so I hope that is clear. How do we use technology to compute that value of area, and then how do we use the data booklet to obtain the answer there. Now, just to check back again what we obtained before this while we are using technology. Okay, just let me check back one more time. You can see that using the technology itself, we are able to get 0.7694. So that is quite a close numbers here. The technology is more accurate because they take into more decimal places than what we are getting from our data booklet. Right? So I hope that is clear. Either use the technology or you can use the data booklet, depending on how accurate your data booklet that you are looking at. Right. I hope that is clear. We have fully completed these questions. Next example, example number 5 here. As usual, we are also given probability density functions here. The first one should be quite easy. We'll work this through very quickly. So to get the distribution functions fx, okay. Then the second part will be there is another continuous random variable given as y, and then relationship between the continuous random variable of y and x is given as such. We are going to answer the following properties that relates to this relationship. Okay, now first one. Now by considering this domain here, we are going to work out its distributions function, which is actually given by this, or by these definitions basically. So I'm going to do it directly this time. So 4t squared dt, that will be from 0, because the lower boundary is 0, up to x. And then that will be a t4 x 0. So that will yield just x to the power of 4. Now that should not be a problem. And then finally, don't forget, write down a full descriptions for your distribution function, which is given as such. That will be 0. For any x value that is less than 0, that will be x to the power of 4. For any x value lying between 0 and 1. And then of course the total area under the graph for all that region must be equal to 1 for any x value that is greater than 1. Right? So I hope that is clear. That is the first one. Okay. Now second one, right? Now we are referring to this relationship here. Y is related to the variable x in such a setting. And then they want us to use this notation hy represent the distributions function of y. Okay, we need to find the first one, the distributions for y. So distributions for y is denoted as, based on the definitions again, that must be a y less than the discrete value, sorry, the continuous value here, y, and then which is given by, because y is related to x in such a way, we can actually make use of its function if you have that probability density functions that relates to continuous random variable y in this case. For instance, you can actually do it in such a way. For instance, negative infinity to a y here. But the main problem is we have no idea what is the density functions that represent the continuous random variable y here. So we can't actually apply its definitions here. Therefore, we're going to make use of this relationship here. Now the y is written as it's given as x cubed, and then that indirectly can be written as y to the power of 1/3 here. And then there you have it. And then we notice that this format looks very similar to this. it says that probability of x less than x here is given by this distribution function. Therefore, we can write this as this is the distribution function for x if we substitute this as our input here. Right? And then based on these distribution functions, we know that this one must be y to the power of 4 over 3 here. For any domain, now that's another issue that we need to clarify here, because if you are using the density functions for x, the domain is given as such. The domain for y, for the distributions functions now, will be given as the cube of the value for x here. Now anyway, because it's 0 and 1, we are quite lucky in this case. The y still lie between 0 and 1, because 1 to the power cube is still a 1 here. And then finally, before we end here, you must remember to write down the full descriptions for cumulative distribution functions that represent the continuous random variable y in this case. As usual, it's a typical task, a typical routine, I would say here. Y would be less than 0, and then that will be a y 4 over 3 for any y lying between 0 and 1, and then finally for any y value that is greater than 1. Now that will be our distributions functions for random variable y here. I hope that is clear. The third question. Here we need to work out the density functions, knowing that the distribution function is given as such. Now the relationship between the density function and its distribution function is given as such. So the density function is the derivative of the cumulative distributions function. Now of course in this case, since the variable, the continuous random variable is y, so we're going to differentiate this with respect to a y. And then I will just concentrate on differentiating this, because differentiating that for this interval and this interval will yield the same result as 0 here. That would be the same as differentiating this y 4 over 3, and then that would yield 4 over 3 y 1 over 3. Okay, now there you have it. That is our density functions. Again, don't forget, you have to give a full description about your density functions. Now, according to our differentiations, if we differentiate the other intervals, it will always yield a 0 for any value that does not fit in this domain. We will write down otherwise. Okay. Now the one that fit in this domain here would be 4 over 3 y 1 over 3 if it satisfies this domain. Alright, now that will be the answer for number 3. I hope that is clear to all of you. Okay, alright. Now we are ready to answer the next one. Question number 4. Now, just for reference, I'm going to rewrite the distribution functions that represent continuous random variable x and y here, just for our reference. For number 4, we are interested to find the probability of a random variable x less than 0.5 here. Now, we can make use of our distributions function here. Okay. Now that would be f 0.5. Okay. Now since x is within this domain here, so we can substitute into this piecewise function, which is 0.5 to the power of 4 here. That is actually 0.25 by 0.25. So that's actually 625. 625, that will be 0.0625. 1, 2, 3, 4, 1, 2, 3, 4. Yep, so I assume that number is correct. Just let me check using my calculator here in case I get the wrong answer here. Okay, 0.0625. That would be great. Now there you have it. That is the answer for number 4 here. For number 5, the probability of y less than 0.5. Now for this, we're going to make use of the distribution functions that relates to a continuous random variable y here. That will be h 0.5 instead. And then that would be 0.5 raised to the power of 4 over 3 here. Okay, I hope that is clear. This one, yeah, definitely not going to use any mental math here. Okay, I'm not actually good with the mental math. Anyway, here we'll use a bit of the technology to help me to work this out. Okay, so that would yield 0.3969 then, if you want to leave it to the 4 decimal places or 3 significant figures if you like. Right? So I hope that is clear. Now we are done with example 5. We're going to move on to the next one. Step 6. Now example 6, we are given the graph that represent the probability density functions. Now the piecewise functions become more interesting. There are more layers in, or you can say there are more pieces of functions involved here. Based on the graph, we have two main functions we are dealing with, the straight line equations. Both are straight line. One is horizontal, one with a certain gradient. The gradient is given by k divided by 2 here. A domain is given as such from 0 to 5. Now the density functions take the value of 0 to 5 here, but it's been split into two different conditions. Okay, now the first question is we need to find the k and show that the function f is given as such. Okay. Now that shouldn't be a problem at this point because it's a straight line equation. And then knowing that this is a probability density function. Okay? Now therefore the total area here must be equal to 1. So we're going to make use of that. We're going to make use of this property here, whereby the sum of the area from 0 to 5 must be equal to 1 here. Indirectly, it means the area under the graph. Now that is typically a half multiplied by a 2 multiplied by a k here. That is the area of a triangle. And then you can add up the area for the rectangle or square here, I'm not very sure. So we have 3 multiplied by k is equal to 1. Then therefore that k must be equal to a quarter. Okay, so I hope that is clear. That's how we find the k easily. And then next we're going to show that the piecewise functions can be written as such. Okay, now to do that we're going to concentrate on this interval. For that interval of I'm going to write down, consider the domain of x lying between 0 and 2. Okay, now that is given by this straight line equation. Is quite easy. It passes through the origin. Therefore that functions must be fx equal to mx plus c, but there's no c here. The gradient, we can obtain the gradient quite easily. So the gradient is actually 1/4 divided by, because this is 1/4 here, divided by 2. So therefore the first graph can be represented as 1 at x. Now then we are going to consider the second domain. Consider the domain between 2 and 5 here. Yeah. For this is much more easier. The functions must be given by a horizontal straight line. The k is actually 1/4, and then there you have it. That is 1/4. And then finally, we're going to provide a full descriptions for our probability density functions. We can write as such. Okay. So there are two typical domains we have to describe here. So the first one is this, which u 1 over 8x for the domain lying between here, and the other one which is quarter for the domain lying between 2 and 5 here. Right. Now you'll notice that writing less than equal to 2 here, there's a conflicting domain. So therefore, to ensure continuity, usually we prefer to write separately. So if you like to represent the first part as equal, then the next one we should drop the second equal sign. So it should be x less than or equal to 5 here. And then finally, of course, it'll be 0 because this graph only exists within this domain, any other value. Okay, and then there you have it. We managed to prove this, and then we are done. Right? So I hope that is clear. All right. Now next we're going to answer the following subsections. The first one being find the probability density functions of y. Thereafter we're going to show that the expected value for y is given as such, and then finally we're going to work out the median of y. Not work out, to show that the median of y is the square of the median of x. Alright, that will be very interesting to functions here. Starting from this part here, we're given a random variable y is related to x in such a way. As usual, we're going to follow the same routine here before we try to work out the probability density functions for y. We are going to work out the distributions functions for f here, for x, for the random variable x here. Now we're going to work out the first one, random variable here. Right. Now that will be given as such, given by these definitions again. I'll just rewrite that one more time for us to follow. From negative infinity to x here. But because this function has a few pieces that connect to the overall density function, therefore we have to consider the cases for each one of the domains. So we're going to consider case 1 for x lying between 0 and 2, considering this. Now our fx, our distributions functions would be, from here there will be 1 over 8t dt from 0 to x. And then there will be a t squared over 16 x 0. And then finally we can conclude that as x squared over 16. Now that's the first part. Then the second part, we're going to consider x lying between 2 and 5. Okay, 2, 5. Now for that we are considering this region now, because it's a cumulated area. So we are interested to look at the cumulated area starting from 0 up until x. So we are interested to find this area here. It's a cumulated area. Therefore, we have to consider the first sections of the area. Now, without using any fancy calculus, we know that the first area is given as what do we have here? So that is actually 1/4. I'm going to repeat this. That must be equal to the first area here. That is 1/4. Add up with the area up to x here. Add up the area starting from 2 up to x, but the functions is 1/4 now, dt. So that's how it look like. There will be 1 over 4 plus 1 over 4 t 2 to x. And then if you simplify that, that will be 1/4 plus x over 4 minus half. Yep, correct. So that will be x over 4 minus a quarter, or you can write in the factor form, factorized form. Now, of course, if you are interested with the domain, just want to show this for consider the third domain where the x is greater than 5. By considering this, we are trying to work out the total area here. If you try to find out the total area, now just for testing purpose, we know that the first area is a quarter, and then the next area is a 3 by a quarter, and then you notice that this is actually a 1. So for that, we have completed the definitions for or the descriptions for the distribution function of x. I'm going to write down at this side here. It would be, the first one would be x square. Okay, now before that, just let me see, oops, sorry. Yep, correct. I think I need to include another section here. Just let me clear this up. So it should be written as such. Starting from 0 for anything, any value x that is less than 0. And then after that, the first one will be x squared over 16 for any value lying between 0 and 2. And then after that, we have a quarter x minus 1 for any x value lying between 2 and 5. And then finally, it's equal to 1 for any x value that is greater than 5 here. Now, that will be the full descriptions of the distribution functions that represent the random variable y here. Okay, so I hope that is clear at this point. And then next, we're going to make use of this and then make use of its original PDF to work out the rest. But before that, we have to answer this question first. We have not complete yet. We need to find the probability density functions for y, but we have just completed working out the the distributions functions for x. Still on question 1 here, we're going to make use of this to work out the density functions for y. Now, density functions for y, yeah, I might want to represent this as a g, for instance. So gy is given by y, let's set a y here, is given by this density functions. Of course, if we knew this, then we can actually work this up to a y. But since we don't have, we have to make use of this relationship. That would be py is actually x squared less than a y. Okay. And then that would yield x less than the square root of y. Okay. So here we don't really need to consider the negative of this square root because all the x value are positive here. So we're only interested in this. That will be the same as f square root of this. And then you will notice that this part make use of the distribution functions for random variable x. Now that will be this part here. Okay, now there you have it. We're going to write that down directly, since this is given by 3 piecewise functions. So therefore, we can write this as, I'm going to write down at the side here. Yeah, maybe I'm going to write down here. Okay. Now the first part must be 0, of course. For any y that is less than 0, of course. Less than 0. For the second domain, it would be anything less than. You can see that this is y is the square of x here. So it should be y more than 0 or less than a 4. Okay. Now for that to be true, it must be the transformations of these distribution functions with the input of square root of y. That will be a y over 16. That will be that. And then next, for the next interval, we have y greater than a 4. Oops, greater than a 4. Greater than, less than, so it's not greater than, equal to. It's just greater than. Just let me clear this up, and then we are good. Right, now greater than 4, less than or equal to 25. Because of the square there, all we need to do is just substitute this one into here. We notice that we have quarter square root of y minus 1 here. Yep, and then we are good to go. And then finally, of course, is equal to 1 for any y that is greater than 25 there. So I hope you are clear on this. Okay. Now, second part, the EY, or the expected value for random variable y in this case. Oh yeah, before that, I always miss out. I forgot that I have not answered this question yet. The density functions. Now we know that the density functions y is basically just the differentiations of the distribution function with respect to y here. Now that would actually yield, I'm going to write it down over this side here, is a differentiation of this. So if you differentiate this, it's actually 1 over 16 for the domain lying between 0 and 4. And then if you differentiate this, that is actually 1 over 8. So 1 over 8 square root of y. And then that is meant for y more than a 4, more than a 4. I always say that more than a 4, but I indirectly wrote down that as equal to. Let me write it down there. That is greater than 4, less than or equal to 25 there. Of course, it will be 0 for otherwise. Alright, now we have completed the sections 1. Alright, that's a very long working we are working with, right? So I hope that is clear for number 1. Second subsection here. We need to find EY, or show that EY is actually equal to 10.25 here. Expected value for y is basically just y gy dy. Integrate that from, okay, now this one is basically from negative infinity to infinity, of course. But we have a few piecewise sections that we need to deal with here, right? So that would be, in this case, we're going to perform the first one, dy, from 0 to 4, of course. And then don't forget the second one, we need to multiply that by y also. That will be a square root of y over 8 dy. That is from where to where? Let me see, 0 to 4, 4 to 25. And then from here, okay, sorry about that. Just let me, okay. So this is the definitions of the expected value. We are going to complete this. This one will be y squared over 16, 0, 4 here. And then this is 3 over 2, 2 over 3. So that is 1 over 12 here. Y 3 over 2. 25 over 4. 25 from 4 to 25 here. And then this one is actually 1 over 2. And then this one we will see what do we have here. 5, 25, 1, 2, 5. 12, subtract off with a 2, 8. 8, 12 here. Okay. So if I use my calculator to compute this, okay, just let me check that one more time. So I will have 1 over 2 plus 125 over 12, subtract off with 8 over 12 here. I will get, this is what I have here, I will get 41 over 4 here. So if you convert it to decimal number, it must be a 10.25. Alright, so I hope that is clear at this point. Alright. Oops, I always pick up the wrong 2 here. Number 3, we need to show that the median for y is the square of the median of x. Now we're going to find out the median for y first in this case. Now since the gy, okay, now I've accidentally removed off my gy just now, so I'll just rewrite that one more time. In this case, my gy, where should I write that? Maybe it's best if I write down my gy over here. My distributions functions for the y itself is given by this section here. If I recall it correctly, it should be that will be the integrations from here. That will be a y over 16. Okay. I'll try to ignore the 0 in this case. Now the second one will be from this one over 16. Okay, just let me see that. That is y. Okay, y, yes, correct. So the second one is 1/4 of square root of y. Yeah, okay. So I just need to pick this up to work out the next section. The median of y is the square of the median of x here. Just let me double check in case I make any mistake here. Yep, okay, that's it. So median for y, okay, I'm going to just use a formal notation here. The m represent the median. Okay, so I'm going to work out the median for x first. The median for x using the distributions for the random variable x should be equal to 0.5 here, and then that should be 50%. Okay, 50%. We can actually try this out. Okay, now before we do anything, this is a bit challenging because it involves two functions here. Okay, yeah, but anyway, if you refer to the original graph here, the first part represent a quarter. So this area is quarter. This area is quarter. I just label that. This part is a quarter. But our median is located within the area of 50%. 50% of the area. This is only 25%. So you need 50%. Most probably it's going to cross over to the second function step. So since we know that is the case, we're going to work that out using this one here instead. So there will be 1/4 m minus 1 equal to 0.5. And then from here we should be able to work out the m itself. That is a 2, imply that the m must be equal to a 3. So it's around 3 here. So median for median, do write down in the conclusion, median of x is mx here, just to make a difference, is equal to 3. Alright. Now the second part is we're going to work out the median for y. Now they are using gy instead. Median for y in this case must also be 0.5% here. Okay. Now from here you can figure that out, which regions that actually give us the 50%. Okay. So if you look at this, the first region would still be a quarter. Yeah, still be a quarter in this case. So that means it should cross over to the second domain. knowing that it cross over to the second domain, we're going to use this instead. That will be a quarter my square root minus a 1 must be equal to 0.5 here. My minus 1 must be equal to 2. And then therefore the my must be equal to a 9 here. Okay. So it should be 9. And then from here, we can conclude that therefore the median of y must be the square of median of x. And then that conclude our discussions. I hope that is clear to all of you. Okay. Let me try to work out another few more questions. Right? Okay. I'll see you in a short.